Hi everyone. Now we're going to solve equations with two or more log expressions and no non-zero constant term. It's okay to have a zero here. Okay, so we're going to solve this equation. 2 log of x minus log of 3x equals 0. Now, it turns out this 2 is really in the way. So what can we do with this? We can use the power rule. This time, it's a basketball. And we get log of x squared minus log of 3x equals 0. And then there are a couple of different things we can do. Now, the fact that we have a 0 here helps a lot. We can easily separate the logs. And that's strategy 1, to separate the logs. We're going to add log of 3x to both sides. So we get log of x squared equals log of 3x. Don't just drop the logs. Although that might coincidentally work in this example, it's a bad idea because often you'll mess yourself up if you try to do that. There's no rule that says that you just drop the logs, and what's happening with the 0 anyway? Okay, we can add this to both sides. That's good. Log of x squared equals log of 3x. Now here, we're dealing with a common log, log base 10, but in a way, it doesn't even matter. As long as it's the same type of log with the same base, we can basically drop the logs because it's the one-to-one property. Log of x squared equals log of 3x. We can, by the one-to-one properties, we can set these arguments equal to each other. We drop these logs and we get x squared equals 3x. Remember now that instead of dividing by x, which is a bit risky, it may be safer to isolate 0 now. So let's subtract 3x from both sides. We get x squared minus 3x equals 0, and then factor on the left. When you factor the left-hand side, you can factor out an x, and then you get x minus 3 over here. To solve this equation, where this equals 0, you set each factor equal to 0, and we get x equals 3, or x minus 3 equals 0, in which case x equals 3. But then, as you can see, we're going to have a problem with x equals 0. And why is that? Because we have to check. The 3 turns out to check out. But the 0 here, if you try to check it out to the original, going way back up here, whether you try to plug it into here or here, you're going to have a problem because in the original equation, when you check out x equals 0, then you're attempting to take log of 0 over here and also over here. If you try to do it for even one of these, you're bad, let alone both. So the 0 does not check out. You're going to blow this thing up. It turns out the 3 does check out. And in fact, you can use log properties to help verify that. But the fact that x equals 3 makes both the arguments positive here, that's a great sign. Literally, a great sign. So even though we have two tentative solutions, the 0 we must reject. Okay, let's make its rejection very clear, like a bad date. Let's reject it. We reject x equals 0. Reject the 0, get you a hero. X equals 3. That's our hero. It's our sole solution. Bear in mind, we could in principle have two solutions, but it turns out the 0 is rejected. All right. Now there's a second way that we can approach solving this equation. Log of x squared minus log of 3x equals 0. We could use the log properties. Condense the left-hand side. The difference of logs is not the log of the difference. It's the log of the quotient. Log of x squared over 3x equals 0 by the quotient rule for logs. Now here, let's remember that the implied base here is 10, right? It's a common log. If you don't see a base, and it's not generic, we assume it's 10, all right? So we get log base 10 of x over 3 equals 0. Now over here in my work here, I went ahead and canceled. X squared divided by x, we get an x on top. Because I made the observation here that 0 cannot be a solution. So I made the observation early on, hey, I know that we're going to have a problem when x equals 0. So I'm just observing that now. X cannot be 0. In which case, I can do a clean division. X squared divided by x always equals x, as long as x is not 0, which I note here. Under this note, I can now write this. Okay, and then we zigzag. We put this log form into exponential form. 10 to the 0 is x over 3. We zigzag. So what I just said was going to exponential form. In my notes here, I decided to kick in a base 10. That's fine. Base 10 exponentiation. 10 to the this equals 10 to the that. All right. Here, from the inverse properties, 10 to the log base 10 of x over 3 is x over 3 itself. And 10 to the 0 is 1. Now, we could have done exponential form. I'll write that out. If you go to exponential form, 10 to the 0 is x over 3. All right. Switch it around, and we get that. 10 to the 0 is 1. X equals 3. Multiply 3 on both sides. X equals 3. And then let's try to check this out. All right. X equals 3. Try to check it out. Well, the fact that we're only taking logs of positive numbers, that helps out, but you should go all the way and check it. 3 is the only solution. That's the solution set. Okay. So things can be a bit tighter if you have a non-zero constant term. So for example, log base 15 of x plus log base 15 of x minus 2 equals 1. Now you might think that the base 15 is the problem. Actually, no. It's more the 1, because that kind of binds our hands more. So here, it's not so easy to separate the logs in a nice way, because you have that positive 1 term kind of hanging out there. So separating the logs isn't so helpful, because you have that plus 1 over there. So instead, we're going to go straight to condensation. We're going to use log properties to condense the left-hand side. We have the same type of log, we better, otherwise we'll have to use like the change of base property, but we have log base 15 for both these terms. We have here the sum of logs. The sum of logs is not the log of the sum, it's the log of the product. We use the product rule of logs. Log base 15 of the product, x times the quantity x minus 2, all of this equals 1. And then you could either multiply this out or do the zigzag, go to exponential form. (15 to the first is this product. And then I turn it around. 15 to the first equals this product. And then we can work out the product. X squared minus 2x equals 15. We could have multiplied out back up here. Now, I make a comment over here, because a common student error is that when students see something like this, they just assume they can set these things equal to 15. No, we have a zero factor property. It's true that if we have two numbers represented by a and b, and if I tell you that their product is 0, then you know that a is 0 or b is 0, maybe both are 0. But if you have two numbers, let's say, that multiply to 15, it's not the case that one of them has to be 15. For example, 5 times 3 will equal 15, even though neither factor is a 15. So do not set these two factors equal to 15. That's wrong. That's wrong. So sorry, folks, but you're going to have to unravel this, isolate 0, and then you got to factor. You got to factor back. This factorization won't help us. multiply it out. X squared minus 2x equals 15 to the first is 15. Now you want to isolate 0 on one side so you can use the zero factor property. It's a zero factor property. So subtract 15 from both sides. Don't say move. X squared minus 2x minus 15 equals now 0. We want that 0 there. Because then, when I factor this, those factors are useful. Because then we can use the zero factor property. When you factor this old school, or you could use the quadratic formula, but you get x minus 5 and x plus 3. Set these equal to 0 and solve. But remember, after you do all that, what do you have to do? You're going to have to check. So when you set these equal to 0, you get x equals 5 from this factor, x equals negative 3 from this factor. You don't have to show the intermediate steps. I'll believe you. Now, it turns out the x equals 5 checks out. If you plug 5 into the original here, we have 5 here, we have 3 here. Oh, and we can actually check it out fairly quickly. Log base 15 of 5 plus log base 15 of 5 minus 2, does that equal 1? Well, 5 minus 2 is 3. And then we could use the log properties. The sum of logs with the same base, the sum of logs is the log of the product. Log base 15 of 15 times 3. Does that equal 1? Well, 5 times 3 is 15. And lo and behold, log base 15 of 15 is 1. That checks out. The 5 checks out. As for negative 3, in a way, it's kind of easy. Here's a red line here. The negative 3, go on up, up, up. Go on up, 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 up. Check it in the original before you got your dirty hands all over it. Okay, we're trying to plug in x equals, what, negative 3, right? Oh, you're dead. Whether you plug it into here or you plug it into here, either way, you're dead because you're trying to take a log of a negative number. Right there, you're dead. The sad thing is, though, is that, see, if you were to plug into here, that could be misleading because when you multiply two negatives, you get a positive. This is a demonstration as to why you got to plug into the original equation, not even the next step. All right, in any case, negative 3 is rejected. The 5 does check out, as I mentioned in more detail over here. And the negative 3 does not. Here's our solution set. Okay. So that is chapter 3 on exponential and log functions and equations and models. Next up, trig.